Welcome to UMSS Chemistry Academy. If it's the first time to watch my tutorial sessions, don't miss subscribing to my channel to have all updated videos. In this video, we'll talk about the basic concept of polarity, a main factors that affect polarity, and how to determine the polarity in polyatomic molecular compound. So, let's go. The basic concept of polarity is clear while dissolving an ionic compound like NaCl sodium chloride salt. The crystal lattice of this salt includes sodium ions Na+, which are cations, and chloride ions Cl-, which are anions. So, how does the dissolution process happen? Let's see in this animated video. Sodium ions are pulled by negative poles of water molecules, and chloride ions are pulled by positive poles of water molecules. So, let's explain the reason of water molecule polarity. In water molecules, the electronegativity of oxygen is 3.5 and for hydrogen is 2.1. So the electronegativity difference will be equal 1.4. This difference in electronegativity is enough for oxygen atom to pull the bonded electrons, and the electron density will be high in oxygen atom. So oxygen atom will acquire a partial negative charge, and the hydrogen atoms will acquire a partial positive charges. So the molecule will be divided to two poles, negative pole for oxygen and positive pole for hydrogen atoms. So what's the meaning of polarity? Polarity is an equal distribution of negative charge in the molecular compound due to high difference of electronegativity values, which will make a greater attraction of electron by the more electronegative atom. So what is the main factors that affect polarity in polyatomic molecular compound? Factor 1 is asymmetry, which means the central atom is bonded with identical atoms, like methane molecule CH4, where the carbon atom is bonded with 4 hydrogen atoms. Factor 2, if the central atom has lone pairs of electrons or not. Lone pairs of electrons means the electrons which are not contributing in bond formation, like the two lone pairs of oxygen in water molecule. Now we need to determine if the molecular compound is polar or not. We have 3 probabilities. Number 1, there's asymmetry and no lone pairs on the central atom. Number 2, there's asymmetry plus lone pairs on the central atom. Number 3, no lone pairs and no symmetry. Let's take examples for each one. The first example for symmetry and no lone pair is boron trichloride, PCl3. First, we should learn how to draw the molecular compound by Lewis dot structure. Boron element is located in group 3A in the periodic table, so it has 3 valence electrons. Let us see Lewis dot structure. Boron in the center and bonded with 3 chlorine atoms, and no lone pair on boron atom. The covalent bonds between boron and chlorine are polar covalent bonds, as the electronegativity of chlorine is 3 and for boron is 2. So the electronegativity difference equals 1, which is high enough to form a polar covalent bond. As we see, the geometrical shape of PCl3 is a planar triangle with the same angle between bonds. So each chlorine atom will pull the bonded electrons with the same power, and each dipole moment will cancel the other one. So the net dipole moment equals 0. So boron trichloride PCl3 is a nonpolar molecular compound. Let's see another example, carbon dioxide CO2. By Lewis dot structure, carbon atom in the center and bonded with 2 oxygen atoms, and no lone pair on carbon atom. The bonds between carbon and oxygen atoms are polar covalent bonds, as the electronegativity of oxygen is 3.5 and for carbon is 2.5. So the electronegativity difference equals 1, which is high enough to give the polarity character to these bonds. But due to the geometrical shape of carbon dioxide, which is linear, each oxygen atom will pull the bonded electrons in opposite direction with the same power. So each dipole moment will cancel the other one. So the net dipole moment equals 0. So carbon dioxide is a nonpolar molecular compound. Let's see the third example about symmetry and no-lone pairs. Sulfur trioxide. By Lewis dot structure, sulfur atom is the central atom and bonded with three identical oxygen atoms and no lone pairs on sulfur atom. The bond between sulfur and oxygen is a polar covalent bond, as the electronegativity of oxygen is 3.5 and for sulfur is 2.5. So the electronegativity difference will be equal 1, which is high enough to form a polar covalent bond. Let's see the geometrical shape of sulfur trioxide. It's a planar triangle where the three oxygen atoms pull the bonded electrons in opposite direction. So equal dipole moments will cancel each other. So the net dipole moment will be equal 0. Sulfur trioxide is a nonpolar covalent compound. The last example about symmetry and no-lone pairs on the central atom is methane molecule CH4. By Lewis dot structure, the carbon atom is the central one and bonded by 4 hydrogen atoms where the bonds between carbon and the hydrogen atoms are nonpolar, as the electronegativity of carbon is 2.5 and for hydrogen is 2.1. So the electronegativity difference will be equal 0.4, which is very low to make out or to create a polar covalent bond. So all covalent bonds are nonpolar in methane molecule. Also, there is no dipole moment, so methane molecule is a nonpolar molecular compound. At the end, the final conclusion, the molecular compound which has asymmetry and no lone pairs on the central atom is a nonpolar molecular compound. The second probability of the molecular compound which has asymmetry and lone pair of electrons on the central atom, let's take an example like phosphine PH3. As we see the Lewis dot structure of PH3, phosphorus atom is the central one and bonded with 3 hydrogen atoms with a nonpolar covalent bonds, as the electronegativity of phosphorus is very close to that of hydrogen. So electronegativity difference will be near to 0. So there is no dipole moment and all bonds in this molecule will be nonpolar covalent bonds. But the geometrical shape of phosphine, which is a 3-based pyramid, it will give the molecule the polarity character, as due to valence shell electron pair repulsion theory, the lone pair of phosphorus will make a repulsion with the bond pairs and increase the electron density on phosphorus atom, which acts as a negative pole, and the hydrogen atoms will act as a positive pole. So PH3 is a polar molecular compound. If we take another example like arsine AsH3, it will be like PH3 as arsenic in the same group of phosphorus and has the same geometrical shape like PH3. So arsine is a polar molecular compound. The second example about symmetry and lone pairs of electrons is ammonia molecule NH3. Nitrogen is the first element in group 5a like phosphorus, but nitrogen has higher electronegativity which equals 3. So in ammonia molecule the electronegativity difference between nitrogen and hydrogen equals 0.9. So all bonds in NH3 are polar covalent bonds. And there are two reasons give ammonia molecule the polarity character. Reason 1, the electronegativity difference which is high enough to create a partial negative charge on nitrogen atom and a partial positive charge on hydrogen atoms. So the net dipole moment more than 0. The second reason, the lone pair of electrons on nitrogen atom makes a repulsion with bond pairs and leads to a 3-base pyramid geometrical shape like phosphine and increase the electron density on nitrogen atom. So nitrogen atom act as a negative pole and the hydrogen atoms act as a positive pole. And also, so NH3 is more polar than PH3 and ASH3. As we said in NH3 molecule, boron molecule is a polar molecule, as the electronegativity of oxygen equal 3.5. So the electronegativity difference between oxygen and hydrogen in boron molecule equal 1.4. And the bonds between oxygen and hydrogen atoms are polar covalent bonds. So oxygen atom will acquire a partial negative charge and the hydrogen atoms will acquire partial positive charge. So the net dipole moment will be more than 0. Also, the oxygen atom has 2 lone pairs, which will make a repulsion with the bond pairs and leads to a bent or angular geometrical shape. And the electron density will be high on oxygen atom, which acts as a negative pole, and the hydrogen atoms act as a positive pole. Finally, Due to the electronegativity difference in H2O more than NH3, so H2O is more polar than NH3. The last example about symmetry and lone pairs of electrons is sulfur dioxide, SO2. Here SO2 has the same angular shape like H2O, but here the negative pole will be the terminal atoms, oxygen atoms, as the electronegativity of oxygen equals 3.5 and for sulfur equals 2.5. So oxygen atoms will pull the bonded electrons and acquire a partial negative charge and acts as negative poles. And sulfur will acquire a partial positive charge and act as a positive pole. So the net dipole moment will be more than 0. Also, the electronegativity difference between oxygen and sulfur equal 1. So the bonds in SO2 are polar covalent bonds. Finally, SO2 is a polar covalent compound. Let us see the last probability, which is no symmetry and no lone pair on the central atom in the molecule. We'll take an example pH2F. Here there is a high electronegative fluorine atom, as the electronegativity of fluorine equals 4. So fluorine atom acts as a magnet and pulls the bonded electrons and acquires a partial negative charge. The other atoms will acquire partial positive charges, so the net dipole moment more than 0. Also, the bond between fluorine and boron is a polar covalent bond, as the electronegativity difference equals 2. And the two bonds between boron and hydrogen atoms are nonpolar covalent bonds, as the electronegativity difference near to 0. So the final conclusion, if the central atom is bonded with non-identical atoms and has no lone pairs, and the net dipole moment more than 0, so the molecule will be a polar one. Finally, thank you for your watching. Don't miss subscribing. See you later in other tutorial sessions.